In this segment, I want to start talking about gravity. We're going to revisit this topic a couple of times as we go through this unit. But for now, we're just going to do a quick introduction and talk about a really interesting thing called freefall. So, gravity. What is gravity? Well, gravity is a force that pulls downward. Well, I haven't officially defined force yet, but a force is not too bad to understand. It's just a push or a pull. It probably doesn't mess with your definition too much, right? So, a force is a push or a pull, and gravity is just a force that pulls downward. So gravity is pulling on me downward, and it's keeping me stuck to the floor. If I drop this ball, gravity is responsible for pulling it downward. And you know what? If I drop a rock, gravity pulls it downward. If I grab a piece of chalk, gravity pulls it downward. Everything, gravity just pulls down. That's gravity's whole job in life. It pulls things downward. Okay, so weight is how we measure that force of gravity. If I go stand on a scale, it's going to say 180 pounds about. What does that mean? It means that gravity is pulling on me with a force of 180 pounds. It turns out that pounds is a way of measuring force. Okay, so 180 pounds, that's my weight. That is a measure of the force of gravity pulling on me. Something else like, I don't know this. I've got this rock right here, right? This rock, I don't know, it's maybe a 20-pound rock. Well, what does that mean? It means that gravity is pulling on this rock with a force of 20 pounds. Okay, so with that in mind, here's a quick question for you. Does gravity pull harder on heavier objects, harder on lighter objects, or does gravity pull the same on all objects? Why don't you give this some thought, pause the video, and I'll see you on the other side. Okay, hopefully you've had a chance to think about this just a little bit. Here I have a small rock. I think we could probably all agree that this rock is not as heavy as this rock, right? So I got my big rock and my little rock. Hopefully we all agree that this rock is heavier than this rock. Remembering that weight is the force of gravity pulling on an object, I can't really just give this to you to hold, but I don't think I'm going to have to try too hard to convince you that it is harder for me to hold this rock up than it is for me to hold this rock up. In fact, my arm is getting a little bit tired. Getting a workout here, okay? So, which one is gravity pulling harder on? It is absolutely pulling harder on the heavier rock. I can just feel it. Like my arm is just straight up getting tired, and this arm just straight up isn't, right? So I can feel gravity pulling very hard on this rock and not very hard on this rock. So, which rock does gravity pull harder on? Definitely the heavier rock. So gravity pulls harder on heavier objects. When I ask this question in class, a lot of times people pick C. And I suspect that the people who picked C have had another science class where they talked about this. You're on the right track, but you're thinking about the wrong concept. It's not the force of gravity that's the same for all objects. It's something different. Okay, so hopefully I've convinced you gravity pulls harder on the big rock than it does on the little rock. So if I was to take these out and I was to drop them, which one do you think would hit the ground first? Well, we could just think about it. That's what Aristotle did. Aristotle was like, hey, this one's heavier, gravity's pulling harder. This one's going to fall way faster. Aristotle said, hey, if this rock is 100 times heavier than this rock, then this rock will fall 100 times faster. It totally makes sense. I can just feel that this is way heavier than this one is, right? So it should fall way faster, right? So the Greeks, they said, great job, Aristotle, you're a genius. Let's go have some wine. But remember, Galileo was the first modern scientist. And we say that because he emphasized observation. Galileo wasn't content to just have a good idea. Galileo said, okay, Aristotle, let's give it a shot. You think this one's gonna fall way faster than this one because it's way heavier? Well, let's just try it out. Kind of crazy it took people 1,600 years to decide to try it out. You and I can do it right now. Let's go try it out. So we just tried that out. We dropped the big rock and the little rock, and hopefully I've convinced you that they fell at the exact same rate. They hit the ground at the same time. You know, like I said, Galileo was the first person to try this. People have been thinking about it for hundreds of years. But Galileo said, let's try it out. And the story goes that he dropped a big lead ball and a small lead ball off of the Leaning Tower of Pisa. And when they hit the ground at the same time, the crowd that had gathered didn't even believe it. They thought he was up to some sort of witchcraft or something. But it's totally true. It's really surprising. But wait a minute. How is that even possible, right? Aristotle's idea, it makes sense, right? I mean, gravity pulls harder on this one than it does on this one. So what gives? Is there anything else that's different about these two things? There is, right? There is. In order to wrap our brains around this, we need to have a new idea. And that new idea is inertia. What is inertia? Well, you may have used this word in your regular life, I don't know. But inertia is an object's resistance to change in its motion. You know what? It's actually the same as an object's mass, which is how much stuff makes up an object. So, you know, we could compare a couple of objects, like my rocks here, right? This rock is very heavy. It has a lot of inertia, right? But inertia isn't what I'm feeling when I hold it out here, because I'm not trying to change its motion. If I shake it, then I can measure its inertia. Okay, it's hard to change this thing's motion because it has a lot of inertia. Compare that with this rock. This rock has much less inertia. It's much easier to change its motion. See, look. See, I can change its motion real easy. Try doing that with this. Oh, you can't really do it. Okay, it's much harder to move this. It has much more inertia. But any object with mass has inertia. This chalk has a small amount of inertia. The nitrogen molecules that make up the air in this room have a very small amount of inertia. But they've got some. Pencil got inertia. I don't know. Yeah, golf ball got inertia. Here's a rag. It's got inertia. Everything that has mass has inertia. So, if this rock is 50 times heavier than this rock is, well, guess what? This rock is 50 times harder to move. If this rock is 50 times harder to move, but the force of gravity on it is 50 times greater, and this rock is 50 times easier to move, but the force of gravity is 50 times less, guess what? It perfectly balances out. So more inertia, but more force of gravity. It just balances out perfectly so that both rocks have identical accelerations. It just works out perfectly. It's kind of amazing, actually. When there's more inertia, gravity also supplies more force. If the only force acting on an object is gravity, then we say that the object is in freefall. Any object that is in freefall always has the same rate of change of speed. And that is its acceleration. It's always the same. And what is the acceleration of something that's in free fall? It is negative 9.8 meters per second squared. That means that its speed is changing at a rate of 9.8 meters per second every single second. Why negative? Because gravity pulls down. Right? If I drop this ball, it will speed up in the negative direction. That's what the negative acceleration means. Now, we have to be a little bit careful here. Free fall. Is this free fall? Now, let me back up a second. In this case, we're going to ignore air resistance, okay? And if we're talking about small rocks falling for fairly short distances, then that's a totally reasonable approximation. It turns out that the air resistance acting on these objects is pretty small, which is why my big rock and my little rock hit at the same time. So, is this free fall? Ignoring air resistance, okay? For this next discussion, we're going to promise to ignore air resistance, okay? Was that free fall? Well, not when it was in my hands, because then I was applying a force to it. But as soon as I let go, then it absolutely is free fall, right? Again, ignoring air resistance. That is free fall. Now, what about this? Is that free fall? Well, maybe you're saying, well, not on the way up. but certainly on the way down. Because on the way down, it's just the same as this, but it's just the second half. What about the way up? Are there any forces acting on the ball other than gravity? And the answer is no. There are not any other forces acting on the rock, except for gravity, on the way up either. Therefore, it is in free fall. Free fall means there are no forces other than gravity acting on the object. So this object is in free fall. When it's on the way up, when it's on the way down, and even when it pauses very briefly at the top of its flight. Always free fall, except when it's in my hand. Now, some of you might be saying, well, but no, you had to put a force on it in order to make it go up. There's another force besides gravity. Well, that's true, except for how long does that force last? Does that force persist after it leaves my hand? Remember, a force is a push or a pull. Once this rock leaves my hand, am I pushing or pulling on it? I'm not. Once this rock leaves my hand, I am not pushing or pulling on it. There is no force on it after it leaves my hand. And, I can't affect the motion of this rock without touching it, because I'm not a Jedi. Which means that once it leaves my hand, I'm no longer putting pushes or pulls on it, and it is in free fall. So, this is free fall. This is free fall. How about this? You bet, that's free fall too, when it's not in my hand. It's free fall when the only force acting on the object is gravity. The International Space Station, an amazing human achievement. It orbits the Earth every 90 minutes. Is it in free fall? Yeah, it is. It is. And what is the force that keeps it rotating around the Earth? It's gravity. Without gravity, it would just head off into space. So gravity is what keeps it orbiting the Earth. Therefore, the International Space Station is also in free fall. How about this? If I drop a rock at a piece of paper, which will hit the ground first? Well, maybe you're thinking this is a trick question. Let's see. I got here a piece of paper, and I got here a rock. So, ready? Here we go. You couldn't see the ground, but you could definitely see that the rock was falling a heck of a lot faster, right? So that rock was straight up falling faster than the piece of paper. So which one hit the ground first? Totally the rock. Well, why? What's different here? And the answer is we just can't ignore air resistance, right? It would be a ridiculous approximation to say, oh, I'm going to ignore air resistance when I drop a piece of paper. No, that doesn't even work at all, right? Air resistance is a huge force. And so this piece of paper is by no approximation even close to in free fall. But what if I performed this experiment without any air? Then what would happen? I have a pretty interesting video to show you. Check this out. So here what we're going to see, we are going to see David Scott, who is an astronaut on Apollo 15, and we are going to see him dropping a feather and a hammer on the moon.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Okay, and now let's check out a video done in a very large vacuum chamber at NASA. This is the largest vacuum chamber in the world. Okay, so first here we're going to see the feathers and the bowling ball fall with air present. And I don't think anyone's going to be super surprised at what we see here.
Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air.
And so now we're going to see the feathers and the bowling ball fall with no air in the room.
Cameras on, 2, 1, release.
Look at that.
They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down. Gravity.
Okay, so again, this is an idea first presented by Galileo in the 1600s and pretty easily demonstrated here in the 2000s. Okay, here I have a series of questions. And in this series of questions, let's ignore air resistance, which, as we've seen, is a pretty reasonable approximation for a rock falling through some fairly short distance. Further, let's round negative 9.8 meters per second squared to negative 10 meters per second squared. That means that we can go through this series of questions without having to get out our calculators, and we can just focus on the concepts involved. Okay, so here I've got this rock, I'm going to drop it. All right, so right when I let go, what's its speed? Why don't you go ahead and pause the video, and I'll see you on the other side. Okay, so we've got this rock, I'm dropping it. What's its speed right now? Well, 0, it's in my hand. What about right after I let go? Well, has it had any time to speed up yet? No, gravity's pulling on it, sure. But right that split second after I let go, gravity hasn't had time to accelerate it at all. And so, how fast is it moving right when I let go? It is not moving at all. So what is its speed? Its speed is 0 meters per second. It is not moving. How about this one? If I drop a rock, what is its acceleration right when I let go? Okay, so I let go. What's its acceleration? Hopefully, you decided that its acceleration is negative 10 meters per second squared. Because as soon as I let go, the only force acting on this object is gravity. And if the only force acting on an object is gravity, it is in freefall. And its acceleration is negative 10 meters per second squared. Watch out, we can tell that D is not the correct answer because the units are incorrect. D is describing a velocity, not an acceleration, because of the units, so watch out for those. Okay, so now I drop the rock and I let it fall for 1 second. Okay, dropping it, let it fall for 1 second. How fast is it going? Well, we know that 10 meters per second squared means that its speed is changing by 10 meters per second every second. So, after 1 second, how fast is it going? 10 meters per second. At 0 seconds, it was going 0. After 1 second, it's going 10 meters per second. Some of you might be saying, what happened to the negative sign? And I say, good question. If I drop a rock, what is its velocity after it has fallen 1 second? We know that it is going in the downward direction, and so its velocity is negative 10 meters per second. Remember that speed is just how fast, and velocity is how fast and in what direction. So its speed can never be negative because negative indicates a direction, right? If we're talking about vertical motion, remember, negative is down. If we're talking about horizontal motion, negative is to the left. But speed does not include direction. So speed is always a positive number. In this case, the velocity is negative because the object is moving downwards. So how about this? If I drop a rock, what is its speed after it has fallen for 2 seconds? Well, hopefully you agree that it should be 20 meters per second. Right when I let go, it's not moving. 1 second later, it's moving 10 meters per second. 1 second after that, it's moving 20 meters per second. After that, 1 second later, it will be moving 30 meters per second, and so on. Ignoring air resistance and assuming you had a high enough cliff, this would just keep on happening until the object hit the ground. Okay, so with that in mind, why don't you real quick draw a motion diagram for a falling object? And I don't know, why don't you give it 4 or 5 dots? Go ahead and pause the video and give me a motion diagram for a falling object. I'll see you on the other side. Okay, so remember that for an object in freefall, the acceleration is negative 10 meters per second squared. And if we're just talking about speed, we don't care about that negative sign. We don't care about the direction, right? So that means that the speed changes 10 meters per second every second. Which means that if it starts at 0 meters per second, then 1 second later it's going to be going 10 meters per second, 2 seconds later 20, and 3 seconds later 30 meters per second. So what should our motion diagram look like? Well, a series of dots with increasing spacing between them. Notice that in this case, my numbering is here, and I've explicitly said that I'm talking about seconds. Okay, so here are my numbers to indicate the ordering of the dots. In the particle model, we see increasing space here. Well, this is for dropping what? A rock? Sure. Would it be different if I dropped a piano? What does a motion diagram look like if I drop a piano? It looks the same. What about a watermelon? It looks the same, right? So notice I've never said what it is that I'm dropping here, right, in this particular one. And that's because an object in freefall has the same acceleration, whether it's a big rock or a little rock or a Buick or a piano or a cat. Every single one of those items will fall with the same rate of change of speed, with the same acceleration. And so here's a picture of a diver diving off of some diving board, or maybe I dropped a baseball. It doesn't matter. In the particle model, these look exactly the same.